I'm glad to share my recent work with Luca Vicinelli about axion star condensation around the primordial black holes and the microlensing limits. First, I will introduce the background of our project. Then I will discuss the axion star condensation inside the mini clusters. Finally, I will talking about the microlensing limits and give conclusions. Let's see the background first. We all know that the dark matter has composed about 26% of 26% energy density of in our universe, but their nature is still a mystery. The dark matter may consist of QCD axions, probably black holes, or even their combinations, which we will talking about. And here is the action for the axion field, and where V is the effective potential for the axion field, and through this way we can induce the axion particle mass and the self interaction coupling constant lambda. And the second candidate for dark matter is primordial black holes, which originate from the primordial quantum fluctuations. You can see window A is important as the PBH can be the dark matter today, but it's not necessarily needed. And let's see the axion star condensation inside an axion mini clusters. Here is the basic physical picture of our system. After the PBH forms, it will create the dark matter from the dark matter background, and then the axion halo will form around this PBH. This process was governed by the gravity of PBH and the expansion of our universe, which will induce the profile with 9 to the 4th power law. And by using this profile, we can define the turnaround radius RTA as the axion halo density matches the dark matter background density. And then we can use this RTA to define the halo radius, and also we can integrate and then we can integrate the profile of this halo to find the relation between halo mass and the PBH mass. And then after this halo forms, the axion star may condensate inside the center of this system. And here is the typical value of the axion star radius, where alpha is the gravitational coupling between axion particles and PBH. And naturally, we need the size of axion star larger than the size of PBH. Then, which means alpha needs to be smaller than 1, and it will induce the a typical sample that the axion for the axion larger for the axion mass larger than 10 to the minus 9 eV, it will lead to PBH mass smaller than 0.1 solar mass. And axion stars have a typical formation timescale tau gr, which proportional to the mass of axion and the velocity of axion to the 6, and inversely proportional to the axion number density square. And by solving this Schrödinger-Poisson equation, we can find the axion star profile like this. It basically behaves like a uniform sphere, and where B is the typical length of this axion stars. And if we consider axion star condensate in the in that halo, we can find some physical limits for this system. First is the Broglie wavelength of axion particle needs to smaller than the halo radius, and the second is that they need to satisfy the kinetic regime condition to form an axion star, and the third constraint is at least one axion star needs to form inside the halo at a certain redshift z. And the last is the last is also the strongest constraint is that axion star mass is smaller than the halo mass. Okay, by summarizing that, we can find the axion star mass parameter space, where the color band represents the axion star mass with the units of solar mass, and the horizontal axis is the halo mass, and the vertical axis is the axion particle mass. Where the green exclusion region comes from the constraint on the axion star mass, and the blue light exclusion region comes from the measurement of black hole spinning, the black hole spin due to the superradiance by emission the light particles. And this three different color band comes from the different QCD axion models. And this lensing means our microlensing constraint will will operate on the after 10 to the minus 6 solar mass. And we can also find the profile of the axion star inside the mini clusters. We call that axion halo stars. And for these halo stars, we have first just like the dilute case. Then after this density decrease to meet the halo profile, it will have a truncate here as the intersection point. And we can then define the halo star radius at this intersection point. Then we can find their mass reduce relation for different models of axion stars. You can see this black straight line is just the dilute axion star case, and this blue and red line represents the halo axion star case. And you can see for each different branch, it will approach the dilute axion star case when the axion star mass sufficiently large. Because for the large axion star mass, it will correspond to a larger central density. Large central density, it will behave as a very overdense object. Then it can ignore the dilute surrounding environment, so it will behave like just like the dilute axion star in the vacuum. Okay, and for the very small axion star mass, it cannot form because if the mass of axion star is sufficiently small, the profile curve will always below the mini cluster profile. Then it cannot form an overdense regime in these mini clusters. So it will end at the low mass point. And you can see it have a largest radius for our halo star case, which is very different. Lensing limits for the axion stars. Here is the basic setup of our lensing system, where the observer and the lens determine optical axis, and the axion star profile will project on this lens plane. And by solving the equation for the extended object, we can find the microlensing event rate and the total event number for this lensing event with the axion stars. And by comparing the theoretical calculation and the ERAS-2 survey, we can give a constraint on the population of axion stars as the dark matter fraction. And we found that it is too small to behave like a point-like object. And let's give the conclusion. First, axion mini clusters can form via the PBH creation in the early universe, and they will grow up until z equals 30, where before the structure formation. Um, and this mini cluster will follow the 9 to the will follow the negative 9 to the fourth power law. And the second, the axion star can form through the gravitational condensation inside the axion mini clusters and behave more compact than the dilute axion star case. And we found that it have a maximum radius in each certain mini cluster mass due to the non-trivial mass radius relation. And finally, axion star forms inside the mini cluster point-like lens in the microlensing survey. Okay, that's all. Thank you.